Hello everyone. We are Group 8 from class on Fridays. Today, we will be introducing the topic of generation, conduction, and reception of electromagnetic waves. Before delving into the details of our experiments, we would like to provide some theoretical background related to the experiments. Theoretical basis. First, we would like to introduce the fundamental theory of electromagnetic waves, known as Maxwell equations. Maxwell equations are a set of partial differential equations used to describe the relationship between electric fields, magnetic fields, charge density, and current density. They consist of four equations, each addressing a specific aspect of electromagnetic phenomena. The first equation goes law for electricity. This equation describes how charge generates electric fields. The second equation goes law for magnetism. This equation states that magnetic monopoles do not exist. The third equation, Maxwell-Faraday equation. This equation explains how time-varying magnetic fields produce electric fields. And the last one is Ampere's circuital law. This equation describes how electric currents and time-varying electric fields generate magnetic fields. These equations form the fundamental for understanding the generation, conduction, and reception of electromagnetic waves. Electromagnetic wave antenna principle. An electromagnetic wave antenna is a device designed to transmit or receive electromagnetic waves, and its operation is based on the fundamental principle of electromagnetic and wireless communication. Here is a brief explanation of a working principle of an electromagnetic wave antenna. Function of the antenna. An electromagnetic wave antenna is specifically designed to interact with electromagnetic waves. When electromagnetic waves reach the antenna, they induce changes in the electric field and magnetic field on the antenna's conductor elements. This change in the electric and magnetic fields result in the generation of electric currents within the antenna, effectively converting the energy of the electromagnetic wave into the electric signal, or vice versa, converting the electric signal into the electromagnetic wave for transmission. Antenna characteristics. Different types of antenna possess varying characteristics that determine their efficiency and directionality when transmitting or receiving electromagnetic waves. Some antennas, such as directional antennas, can concentrate energy in specific directions, thereby extending communication range. Others, like omnidirectional antennas, radiate or receive signal uniformly in all directions. Imagine there is an upright metal rod with a potential difference applied to its upper and lower ends, causing electrons to accelerate towards the positive end while leaving the other end positively charged due to the lack of electrons. Such occurrence will create a magnetic field in the surrounding space. If the potential difference varies over time, such as oscillating in the sinusoidal function, the resulting magnetic field will also change with time. According to Faraday's law, a change in magnetic field will induce an electric field in the surrounding area. This electric field will, in turn, vary with time, oscillating in the sinusoid function, leading to change in electric flux. This change in the electric flux will induce magnetic fields in the vicinity. This interactive cycle continues, with alternating electric field inducing alternating magnetic fields, and alternating magnetic fields in turn inducing alternating electric fields. This process results in the formation of electromagnetic waves.
In this experiment, we're going to measure the magnitude of the radiation produced by the walkie-talkie. For this experiment, we will use a spectrum analyzer, a walkie-talkie, and two measuring scales for measuring the distance and the angle. So first, we need to set up the spectrum analyzer. We should find out the appropriate frequency range for the experiment so that we can precisely obtain the data of the strength and the frequency. Since we don't know the frequency range of the walkie-talkie, we first press the span button and choose the full span. We can see the full span of this spectrum analyzer is from 0 Hz to 2.7 GHz. Then, the reference level should be set to 20 dBm. Press the amplitude button. Press 20 and press the dBm button. Now we have set the reference level to 20 dBm. So after setting up the spectrum analyzer, we turn on the walkie-talkie by pressing the button on the left. On the screen of the spectrum analyzer, it can be seen that there's a significant spike. Since we want to know the frequency of the spike, we press the marker button and press to peak option. The marker on the screen will show the frequency of the highest spike. So the marker is showing the frequency as 432 MHz. Let's set this frequency as our center frequency. Press the frequency button, press the center option, and press 432 MHz. So now the marker has come to the center. Then we set up the span to 400 MHz by pressing the span button and 400 MHz. So now let's see our trigger level. It gets triggered as soon as it sees the signal. If we change this to single after pressing the walkie-talkie, it will register the frequency, and the signal will be sticked onto the screen. For the second part of this experiment, we first lengthen the antenna to the most. Then, we put the walkie-talkie underneath the antenna. By gradually increasing the height of the walkie-talkie, we can plot the intensity versus the antenna length graph. For a dipole antenna, when it is placed parallelly to the receiving antenna, the signal strength should be the least when compared to 90-degree angle. So for the last part of the experiment, we rotate the walkie-talkie and measure the data. We can plot the intensity versus the antenna angle graph.
Result analysis. Measuring the effects of antenna distance on received electromagnetic wave intensity. We intuitively believe that as the distance of electromagnetic wave increases, the size of electromagnetic wave will be consumed by the environment. So we think the result should be that the further the distance, the size of the electromagnetic wave will continue to decrease. The two pictures above are the results of our predictions. The two pictures use different vertical axis units. This is the result of our experiment. It can be observed that the strength of the electromagnetic wave gradually decreases as the distance increases. However, the data also shows a rebound in strength at certain points. We hypothesize two reasons for this resurgence. First, the lowest point corresponds to the node of standing wave, where the energy is minimal. Second, since radio wave radiates in all directions, some wave directed elsewhere might be reflected back to the spectrum analyzer. We refer to these as interference waves. The impact of this interference wave becomes non-negligible at sufficient distance from the radio source and thus gets detected in our measurement. The relationship between the reception magnitude and the length of the antenna. The closer the antenna length is to half the wavelength, the better the reception and the greater the detection strength. For a normal transmitting signal on a metallic structure of half wavelength, as the signal enters the negative half cycle and reaches the end of the conductor, it needs to reflect back and propagate in the upside direction. The negative half cycle plus reverse propagation becomes a positive signal, which can superimpose to form a standing wave. Thus, the signal can gradually strengthen within this conductive structure, radiating the maximum amount of energy each cycle. In our experiment, the radio wave's length is about 60 centimeters. Therefore, an antenna length of 30 centimeters should be most effective. However, we can see the left-hand side graph. Initially, we did not place the walkie-talkie at the 0 centimeter position of the antenna, which caused some errors. And we look at the right-hand side graph. This is the graph made by the Tuesday class and is aligned with the experimental prediction. The relationship between the reception magnitude and the angle of the walkie-talkie. A dipole antenna is designed to be bidirectional in its radiation. Ideally, a horizontally placed half-wavelength dipole antenna uniformly radiates electromagnetic wave in opposite directions along its long axis. There is almost no radiation of energy in the direction perpendicular to the antenna's long axis. Therefore, we predict the graph to look like the one on the left. While the right graph represents our experimental results, our graph differs from the theoretical one because we incorrectly identified the 0-degree position during the experiment, resulting in our graph being perpendicular to the theoretical prediction. And below are the correct graphs produced by other groups. This is the end for our video. Thank you for your patience.